Okay, welcome. For this lecture, we're going to be talking about control system performance. So, in designing a control system, obviously we have some specific goals in mind for that control system. In order to design anything, we kind of need some sort of measurable parameters that we're designing against, right? So that's really what we're trying to do is determine some parameters we can assign to maybe the response of a control system so that we can use those parameters to drive decisions in the design process. Okay. So some of the basics of control system performance, with any control system, we really just want to make the system respond to a command and produce the desired output. We set the thermostat to a particular temperature. We want that um, thermostat to control the heater or air conditioner or whatever so that the room and the temperature matches what we desire, you know, as soon as possible or in a reasonable amount of time and, staying within some error. So, in other words, in that example, it's really not going to be good if the temperature, shoots up to 200 degrees, then back down to 32, and then settles at our desired 72 degrees. So, in all applications, there's some bounds that we would find reasonable for performance. So, obviously, if it shoots up to 200 degrees, it's going to roast everybody. So, not really a great solution. So, we would, in that type of control system, we would have some requirements for overshoot in this case, right? Also, settling time is another type of parameter we might use. We obviously wouldn't want it to take 36 years for the room to reach our desired temperature, right? So the point here is with all applications, there's some reasonable bounds of performance that we would like to achieve. Okay, and that's going to drive the design of the system. For this particular example, we wouldn't want a heater that just puts out little microwatts of heat for a huge room because the settling time would be years maybe or would never get there. Um, and conversely, you don't want a huge blasting jet engine that's going to take the temperature up to the room up to several hundred degrees before it settles back down. So um, you know the point here is that we have reasonable bounds on the performance of these control systems, and that's really going to derive the design. What does the control system design look like given these bounds on performance? And ultimately, it's going to really drive trade-offs in the design process, right? So, like the just previous example, you had some kind of micro heater, probably very cheap, but not going to work very well. And then there's the jet engine, very expensive, also not going to work very well. But there's a trade-off in there somewhere, right? And there's probably an ideal heater size that you would want, and some sort of control system gain or whatever you want to design that would turn that heater on and off, to regulate the temperature in the room. Okay, I think you guys get the idea. Okay, so let's just consider this control system below. This is a very general control system, right? So G of S is the controlled system, D of S is our controller, and H of S is the transfer function, which is usually in physical systems, we kind of consider that the sensor, right? So it's whatever is, in the case of our room temperature thing, that's maybe the thermostat. It's measuring the temperature in the room and feeding that back into our control system so that the left side of H of S is degrees, right? So this would be degrees. Oh, I'm not set up to draw, but you'd have degrees here on the left. So your error is going to be desired degrees minus actual degrees, and that error is what's going to go into your controller, right? Okay, if H of S in the feedback path is a unity gain transfer function, and the system is called a unity feedback system. So we can always take a non-unity feedback control system and make it into a unity feedback control system by taking this H of S and kind of distributing that around this summation block, kind of like this, right? So when you're going forward, Y of S is a function of R of S. If you do this, you'll find that this block diagram down here does equal the block diagram up here. So it does maintain the overall transfer function of the system, but in this case, the feedback is unity, which can make things a little bit simpler for us. Okay, so again, the purpose of the control system is to make the output follow the command. In other words, we want to zero out that error between the output and our command. So when there's a change in the reference command, we change the temperature on the thermostat or whatever, the controller needs to take that action on that new error signal and make the output track the reference command and zero out that error. So the performance of the control system is really going to be determined by how the system reacts to the change in a command. So let's look at an example. So here's a simple first order system with unity feedback, and really our controller, that D of S, is just unity gain. Okay, so you could maybe say this is kind of a proportional type control system, right? Where the U of S is really proportional to the error. Okay. So in this case, Y of S is the output, U of S is our actual control signal going into our system, and R of S is our reference input, our desired input, our desired output, or our command. And then you can see this would be the error signal out of the summation block. Okay, so let's consider the case of a first order system with this type of controller when the input, the reference input, or the command is changed from 0 to 1 at t equals 0. So we're going to have an instantaneous, if everything's steady state before that, that's going to cause an instantaneous error coming out of this, which is going to drive this controller to output some sort of control signal, which is now going to be proportional to that error, and that's going to go into our system. So, we know from our study of first order responses that this is a pretty typical type response, right? A first order system generally going to have an exponential type response. So this is what we would expect. But what you'll see is the value of K, the gain of this proportional control, is really going to impact the transient response. Not just the transient response, but the response in general of that first order system. So a couple of different plots here. We plotted the response with K equals 5 and with K equals 10. So the orange plot is for K equals 10. You can see it responds much faster and also kind of reaches a little bit different final value, right? I didn't extend these out all the way, but realize that these are going to end up being different final values. Okay, so really that's going to be drivers to, what the design of our control system is going to be. These are going to, K has an impact on the performance of this control system. So in this case, you can look at it and say, well, I would think that K would have a better performance, just in general, looking at the difference from K and 5. With K equals 10, you have a much faster response. You get closer to where you want to be quicker. It does have some overshoot in this case, and well, it does actually not overshoot, but it looks like it's settling onto a final value that's somewhere closer to our desired value of 1 than this K equals 5 control system. Okay, so really what we're trying to do is quantify some of these things like rise time, overshoot, settling time, things that might matter to us in the real world, and how we can quantify those so that we can design our control system. In other words, select our gains or other attributes of our control system so that we meet those desired physical descriptions of the response. Okay, so really we can divide the response into two basic features. First, how fast and smoothly the response approaches the reference. So how fast you're getting to the value you want, and how smoothly, in other words, if you have a lot of overshoot, is a factor. And second, how close to the reference the final value is. So at t equals infinity, what is the actual final value? Do we reach our desired value, or we have some steady state error, right? So we call these features, two main groups of features, transient and steady state performances. So transient would involve what is what does the output of the system do, when it's changing, and then the steady state is, at its final value, what does it look like? Okay, so the transient performance we can assign several values to. We can describe several attributes of that depending on the order of the system. Steady state performance is really simply the final state of the output at t equals infinity. To assess the performance of control systems, sometimes we apply a variety of test input signals. I know you're used to the unit step. We usually use that as a pretty good example. Put in a unit step, and the system is going to have some sort of response to that. That's pretty typical. But there's also a unit ramp, which is described here mathematically, where it's what you'd expect. T, the output is going to be equal to t, where the unit step, the output is equal to 1, and then the unit parabolic input, which is going to be t squared over 2. It's going to have a parabolic type response. And all of these are really designed so that in the Laplace domain, unit step is 1 over s, unit ramp is 1 over s squared, and unit parabolic is 1 over s cubed. So that makes, when you multiply that by your transfer function, that makes the polynomials a little bit cleaner. So that's why we define them this way in the time domain. Okay, so the response of the system to these inputs is called the unit step response, unit ramp response, and unit parabolic response. Typically, and for the purposes of this course, we're really going to be limited to the unit step response in general. Okay, so let's look at that same system we looked at before, where we have a proportional block here, so where the input, the control signal to our system is going to be basically just proportional to the error. Okay, so we can find the transfer function of this. For the unity feedback, we know that that is going to be, this top transfer function over 1 plus that top transfer function. So k over s plus 1 over 1 plus k over s plus 1, that's going to be the closed loop transfer function. Here we can use some algebra, multiply top and bottom by s plus 1, and get a little bit simpler transfer function here. Okay. All right, so we can cross multiply these out, and we get this in Laplace domain. We're starting to get an equation here. And we can basically do the inverse Laplace transform, just like we've done before in the units for Laplace. And we can find the time domain response of this system. Okay? So if we find the inverse Laplace transform, and we assume that r of t is going to be a unit step, so this is making a command that goes from 0 to 1 is kind of what we're interested in for looking at this response. So if we use r of t equals u of s, then we can actually take the inverse Laplace, and we basically get the solution to the differential equation that looks like this. So this is pretty typical, right? This is, you could also think of this as, k over k plus 1, times a 1 minus e to the minus k plus 1 t, right? So this, that's a typical response for a first order system, right? It's 1 minus e to the minus tau t, or t over tau. And here, we just have a gain factor in front of that, if you will, k over k plus 1. So that's going to be pretty key here. If you look at that, you can see that, when t goes to infinity, this second term is really going to kind of drop out, right? Because that's going to decay away, and we're left with just this, what we're going to call the steady state response. And you can see that it's not equal to 1, even with a unit step input. This k over k plus 1 is not going to be equal to 1, which, this could be a problem if you really want to get to your exact final value. This may not be the type of control system you want to use. Okay, so really we have a combination of a homogeneous solution and a particular solution. So we talked about that a little bit when we talked about differential equations. So as t approaches infinity, this homogeneous solution goes to 0. So this is homogeneous. And this is particular, right? Okay, so at t equals infinity, this exponential goes to 0, and this whole homogeneous term, or part of the solution, goes to 0, and the entire solution approaches this particular solution of k over k plus 1. Okay, so this is really the steady state value. So when we looked at those two graphs for k equals 5 and k equals 10, you can kind of see that's why one, was approaching, what's actually going to be 10/11ths, and the other was approaching 5/6. So different steady state values depending on the design of our control system. So another example of, if we do have some error, we can allow for our final value. That's really going to derive our control system design, right? If we have to be within 1%, then we know that for this type of control system, k would need to be 99. So it would be 99 over 100. Now that may have other ramifications that impact performance. There might be some trade-offs, but that's just one example. Okay, and here we can say the transient performance is determined by the homogeneous solution. So how that system behaves while it's changing in time is really going to be determined by the homogeneous. So the homogeneous solution impacts transient performance. The particular solution impacts the steady state performance. Okay, so if we look at transient performance, here for our two examples of k equals 5 and k equals 10, we can plug in those values of k, and here we get, for k equals 5, we can see that we have a final value of 5/6, right? So when this homogeneous solution dies away, we have the particular solution of 5/6. So even though we're stepping the input or the command from 0 to 1, the output, is actually going to be, 0.83, right? And here we're going to be 10/11ths, which is probably what, 0.91, something like that. So you can see that k has an impact on our final value. Okay. Also, you can see that the decay factor is different, right? So for k equals 10, we're going to have a faster decay, so we're going to approach our desired solution probably a little bit faster. We expect it to have a faster rise time than k equals 5. Okay, so that's why in general we said that k equals 10 looked like a better solution. It gets closer to our final value, our desired final value of 1, and also seems to converge on that quicker. So that's why when just looking at the graphs, k equals 10 appeared to be, the better choice. But really what we want to do is assign some actual hard parameter numbers, right? So we can actually compare some of these performance instead of just saying, oh, it looks faster and gets closer to the final value. We want to actually be able to calculate what these parameters are. Okay, so for transient performance, we're looking at up to 4 possible parameters we use to assess that transient performance. And that's these here. So overshoot, if you have a second order system or you have a system with overshoot, we'll have potentially this oscillation type response. So there can be some overshoot, and that amount of overshoot is called M sub p. So notice this is like a percentage, so it's maximum peak output. It's this value, divided by the steady state value, right? So this is going to be a percentage of your steady state value, a percentage over your steady state value. Okay. So if this is 1.2, then this MP would be equal to 20% overshoot. That's kind of how that value works, or 0.2. So in this case, if our steady state value is 1, then this would be 0.2, which is the actual physical amount of that overshoot. But if this is 2 and this is 1.4, it would still be 20%. That makes sense. Okay. Peak time is the time it requires to get to this peak value, the largest value, right? which is the peak of the overshoot. So that's something that we'll be coming up with a formula for. Settling time is going to be the time where your signal stays within error bounds. So if we have this plus or minus error, say we have plus or minus, you know, 5% bounds, that's going to draw, you know, some dotted lines, kind of like this, right? Plus or minus 5%. Well, as soon as our signal is within those bounds for forever, which is right here, right? So after this point, you know, the signal stays within those errors. So that would be our settling time. The first time that, or maybe you could say the last time that your signal is outside those bounds is kind of where that would be defined. Okay, and then we have rise time, which is simply defined as the time it takes to go from 0.1 of your settling time to 0.9, I'm sorry, 0.1 of your final value to 0.9 of your final value. So it's this delta here. That's your rise time. Okay. And keep in mind, and we'll talk about this in a minute, for a first order system, we won't have overshoot, right? We have an overdamped system. Well, for any overdamped system, you know, we're only going to have rise time and settling time. So overshoot and peak time are only for, you know, underdamped or second order type systems where we have, you know, some sort of overshoot. So these four won't always apply to every system. Okay, so let's go back to our really general control system, our controlled system, our controller, and our feedback type system. If we look at the transfer function of this, we have this, right? And we're going to label that GT of S. So this is the transfer function. This is our closed loop transfer function for a very general system. Okay, if we look at the first order closed loop transfer function, this is what we get. We get 1 over tau s plus 1. We can use our inverse Laplace transform, and we can come up with a y of t response to some sort of a unit step input that looks like this. A very typical response, right? We're going to have 1 minus, you know, this decay at t equals 0. This will be 0, and we'll have our typical, you know, exponential type increase, right? Okay, so if we look at some of those parameters we were looking at before, you know, we'll have some sort of response here. We have a rise time that takes our signal from 0.1 to 0.9. So that's going to be this time here, right? We also have our final value, our settling time, we have our settling time, which means that now it's the last point where we're outside of the bounds of some error. So that's this TS right here, okay? So rise time and settling time are both two parameters that would apply to this type of response. Okay, well, since we know for this particular differential equation solution, we have y of t is 1 minus e to the minus t over tau. Okay, so if we take the logarithm of both sides, we can see that we'll get logarithm of y of t, natural logarithm of y of t, natural log of 1 is 0, right? So this would be negative, and then the natural log of this is negative t over tau. So that's going to be equal to t over tau, right? Okay, which is what I showed down here. Okay, and then we can solve for t here, and we get t. So the time is going to be tau times the natural log of y of t. Okay, so whatever value y of t is, we can find the time that, you know, on this curve for these values of y of t. So if we want to find the time for y of t equals 0.632, we could find that time t right here, right? Okay, we can also use it to compare times on this curve. So in this case, if we want to find the rise time, we're basically saying the time at 0.9 minus the time at 0.1. Okay, so time at 0.9 is tau natural log of 0.9. The time at 0.1 is going to be tau log of 0.1. We can actually, since these are logs, subtracting logs is like the same thing as dividing. So we have tau natural log of 0.9 over 0.1, which means the rise time is going to be tau natural log of 9. Okay? So that's just a good succinct way to actually measure the rise time, which is always, in a first order system, is always going to be based on tau, right? That's the parameter that determines the decay factor on this thing. Okay, so we can always calculate the rise time of a first order system if we know tau, right? Okay. And settling time, for a first order system, it's pretty easy, right? We're just basically finding rising to, in this case, 1 minus whatever our error is. So if we have a 2% error, that would be, 0.98. So we're finding the time it takes to get to 0.98. So time it takes to get to 0 minus the time it takes to get to 0.98. So here we're basically saying minus 0.02, right? So we're kind of doing a little bit of math. Instead of doing 1 minus, tau log of 0.98, we're just flipping that around. And if you do that math, you can see the settling time for a first order system is going to be equal to 3.9 tau. Okay, so regardless of, so basically we found that the settling time and the rise time are totally dependent on the value tau for a first order system. So pretty easy to calculate and predict. All right, so I kind of put those in a red box. So if you have homework on control system performance, once you know tau, then you can easily calculate the rise time and the settling time. Okay? So since, like I said before, since the first order system doesn't have any overshoot, then the overshoot MP and TP peak time values are not defined since there's no overshoot. Okay? So tau for a first order system is called the time constant of the system. So obviously it is a factor in determining, the speed of the response, which is going to impact rise time and settling time. Okay. Okay, let's kind of look at the same thing, but for a second order system. This is where it gets a little more complicated because second order system, you're dealing with two solutions, and there's a variety of possibilities, right? You could have a double root, you could have real roots, you could have complex roots, and those are all going to basically result in a little bit different look to the response of your system, right? Okay, so let's look at a typical second order system, and we can do the same manipulations before. Find the transfer function, and we get this k over s squared plus s plus k, which is a nice clean format for second order closed loop transfer function. Okay, so we often refer to the standard second order transfer function, where now we have we've introduced the values of omega sub n and zeta, which are constants, which are consequential parameters within that second order transfer function. So whenever we have a transfer function in this form, where there's no coefficient by the s squared, we can solve for omega n and zeta, and that's basically going to drive some of these transient performance parameters. Okay, so we need to think about what the roots look like. Obviously, we're going to have a little bit different solutions. So first, assume two distinct roots. So we factor this out. Let's assume we have two roots, S1 and S2. We can do the partial fraction expansion, and we can find that, for these two distinct roots, K1 and K2 are given by these values here, and we have this type of time domain response, right? Okay, so two distinct roots, not the same. Well, let's say they could be the same. Two distinct, let's say, well, that was two distinct roots. Now let's look at the case where we have two double roots. So that's where we have, s minus s1 squared. So if you do that math, you can also get a similar transient response, y of t. But you can see here we have the output looks a little bit different. We have this t function here. So this would actually be the solution to that differential equation, assuming we have double roots. So you kind of have to account for both. Two different roots, double roots. Okay. So let's look at the roots of that second order characteristic equation. So down here we have our characteristic equation in the denominator. And this is the differential equation associated with that. Well, if we basically factor out this denominator, we can find a formula for the roots of that in terms of zeta and omega sub n. So if we use the quadratic formula, we get our two roots, s1 and s2. It's going to be this minus zeta omega sub n plus and minus this part under the radical here. Okay. So there's our two roots, and you can see depending on the values of omega sub n and zeta, this radical could have complex values or it could have real values depending on the magnitude of zeta. In this case, if the magnitude is greater than 1 or less than 1, that's going to determine whether this is going to have complex or going to have complex values or not. Okay, so there we just kind of rewrote those roots. Three cases to consider. If we assume that zeta is greater than 0 in general, then we're going to have three cases. Zeta is greater than 1 means that this under the radical is going to be positive, and we have two distinct real roots. Okay. If zeta is between 0 and 1, then we're basically going to have plus and minus. This is going to be a complex, right? So we'll have two complex conjugate roots. And if zeta is equal to 1, then this radical goes away and we have two double roots, right? At minus zeta omega sub n. So there's kind of the three cases that we can have for the second order response as far as roots to the second order characteristic equation. Okay, so if zeta is greater than 1, then we're going to have two distinct real roots. We can kind of plug that in, and we'll get a couple of values. We'll get tau 1 and tau 2 for our solution, and those are given by these fractions here. So this is our 1 over, and then zeta omega sub n plus or minus then that radical, right? Okay. So in that case, our two taus is going to give us a solution to the differential equation that looks like this. Okay, so if these are both real, then we're going to have a couple of different exponential decay terms, right? And then 1. So this would be our typical exponential response. Okay, and these would decay to 0 at t infinity, right? So then we would kind of converge on our particular solution, which in this case is equal to 1. Okay, so the homogeneous solution is in the form of exponential functions, and this is called overdamped, right? They're just going to basically not going to be any oscillation. These are going to trend towards 0 over time, and it might look something like this. So for this particular equation, we can use partial fraction expansion, and we can find these values of tau, and then we can use that to form our time domain solution. And you can see here, it's a combination of this minus 2 e to the minus t and this plus 1 e to the minus 2t. Add those two together and you get something that looks like, this response, right? So you can see no oscillation, it's underdamped. We could calculate the rise time here, we could calculate the settling time, but there's really no overshoot or peak time associated with this. Okay, so that's for two real distinct roots of that characteristic equation. Okay, if we look at the case where eta or zeta is between 0 and 1, that means that this radical is going to have a negative under it, so we're going to have complex conjugate roots, which look like this. And so basically, this is kind of ugly looking, so we can clean this up a little bit. This minus zeta omega n, we're going to call alpha or sigma. And this radical, we're just going to call that omega sub d. That lets us write things a little bit clearer, so we can actually write these two complex conjugate roots as sigma plus j omega d. So if we're going to plot these in the complex plane, this makes it a lot easier, right? If we have our complex plane or our S-plane, you can see that now in our S-plane, we have sigma and j omega, right? Or j omega. That's going to be something we can plot in the Laplace plane pretty easily, right? So this would be sigma plus j omega. Okay. So, and what we'll find is the location of these roots in the S-plane is going to determine a lot about what our system response looks like. So those of you who have had or are taking control systems, you should already know, definitely if you have this sigma is on the left half plane, you're going to have, an oscillation that decays. If sigma is on the right half plane, then, we're going to have an oscillation that is increasing, which is unstable. And that really comes down, to when you take e to the sigma, if sigma is over here in the left half plane, then you're going to have exponential decay instead of exponential increase. Okay, so we'll make some generalizations about kind of the location of poles, but this isn't a control systems design course, so we're not going to get too deep into that. We'll just kind of show how those parameters do impact the transient response of our system. Okay, so for two complex conjugate roots, the solution of our differential equation looks like this. And these are complex conjugates, so S1 is equal to S1 conjugate, K1 is equal to K1 conjugate. Okay, in this case, K1 looks like this. This is the solution. Okay, so you can see we have complex conjugate values here, so we kind of have an e to the j and an e to the minus j. So knowing Euler's law, we know that we can kind of turn that into a sinusoid, maybe after factoring out an exponential factor. We're not going to get too deep. We're not going to get into that at all, but just know that, Euler's formula basically says that, cosine of theta is equal to e to the j theta plus e to the minus j theta over 2, and sine is equal to e to the j theta minus e to the minus j theta over 2j. So Euler's basically just lets us relate complex exponentials to trigonometric functions. I have a whole lecture on the derivation of that. If you're interested, just let me know, but I'm assuming you're not going to want to hear that. So we'll move on and just kind of take this at face value. Okay, so applying Euler's law, you can see here we have e to the s1t, where S1 is going to be a complex number, so think of that as maybe our theta, and then e to the minus j theta, if you will. So that's going to be equal to, some function of cosine of that complex number. So we can do some rearranging. And it gets kind of ugly here. We're talking about, magnitude and phase a little bit. Don't worry too much about this. Just understand that we're just kind of rearranging this, and we're basically getting something that is in the time domain with no complex terms, right? We don't really want to deal with complex exponentials, e to the j type stuff. So using Euler's law basically lets us write the response as a real time domain response. And you'll see what we actually get is we kind of factor out this decaying exponential. This becomes a sinusoidal term. Okay, so really what we get is a exponential and a sinusoidal term. Okay, so this is why if sigma is in the left half plane, you can see this is going to decay, and this will be a decaying oscillation, right? So it'll, look like that. Whereas if this sigma is in the right half plane, in other words, if sigma is positive, then that is going to be exponentially, increasing, which would be bad in general. Okay, so here we can see the response of our system is basically a decaying exponential times a sinusoid, which will look kind of like this, right? So if we have, this 1 here, and let's say k is a negative number, that's how we get some, type of response that looks like that, where we have a final value. Okay, so the magnitude of this sinusoid is decaying over time. It's oscillating with, something related to omega sub d, which if you look back is kind of related to zeta and omega n, right? So it's a combination of both of those, which are in turn related to, if you go way back, those are kind of related to, coefficients of our characteristic equation, right? Okay. Okay, so the homogeneous solution is a sinusoid multiplied by an exponential. Okay, and since in this case sigma is a negative real number, the solution will converge to 0, and we're left with the this basically plus 1, which will be our our final value here. Okay. Okay, so if we have these two complex conjugate roots, this is basically expanding that back out. Our omega sub d is now being shown as this zeta omega n. So we're basically kind of backing out to our, making this y of t in terms of omega sub n and zeta now instead of omega sub d and sigma. We kind of look at this. We have a phase term here with this cosine, which is going to be related to zeta. Not really super important to us right now, but if we plot the location of these roots in the s-plane, right, which is going to be versus sigma and j omega, you can see that s1 is here and s2 is going to be over here. So we have sigma plus minus j omega d. We can look at the magnitude of that, which we're calling omega sub n, right? So omega sub n is the magnitude of that pole location, which is this right here. And really, we can draw some conclusions to what our response is going to look like, depending on this angle theta. So where this pole is in this plane, basically, if they're very close to this j omega axis, this theta is going to be very small. That means that our zeta omega n, which is this distance here, is going to be very small. So we'll be able to draw some general conclusions from just the location of these complex conjugate poles. So this theta is kind of related to the zeta value. The distance between the origin and the pole, so this magnitude is omega sub n. It's not related to zeta, so some interrelation between some of these parameters and or performance parameters we're going to provide, and then characteristics. For purposes of this class, this isn't super important to know all the specifics of this. I'm just trying to give you some background on where this is coming from when we start to calculate these actual parameters that matter to us. So in this case, really, it's kind of important to see that omega n really determines the speed of the response. Okay, because here you have omega sub n here, which is always multiplied by time. Okay, so that's really going to be controlling how this behaves in the time domain. Okay. Okay, so if we look at a couple of examples where omega sub n equals 1, and omega sub n equals 2 for a zeta of 0.2, you can see that, you know, this distance here, remember, was omega n zeta. So you can see we're basically looking at a couple different values for our complex conjugate pairs. For omega n equals 1, I guess that's not really shown here. Oh, it does show here. So this is 1 and this is 2. So for omega n equals 1, we have a slower response, right? The overshoot is the same. The settling time is a little different. Rise time is definitely different. But you can see for omega n equals 1, we have a little bit slower response, a lower frequency oscillation. For omega n equals 2, we have a faster response, a higher frequency oscillation, and a little bit faster decay, right? So all those parameters that we talked about, rise time, overshoot, are really going to be impacted by omega n and zeta in different ways, right? So we know that omega n is going to impact the decay. Well, we just kind of look back here and you can see the decay is really a combination of zeta and omega n. Final value in this case is going to be 1, but so don't get too wrapped up mathematically in translating this to some of those other parameters. We're going to come up with, I'm just going to give you the formulas for calculating those other transient parameters based on basically omega n and zeta. This just kind of shows mathematically that, you know, that transient response is related to eta and omega n. It's kind of all over the place here, so it's not super obvious how that's going to relate. You know, zeta is going to determine, you know, whether you have what type of roots you have, which will generally drive the overall response. You know, omega n is going to be strongly related to, you know, how fast you oscillate. That's why it's kind of written as omega, right? It's kind of like a frequency. So that's going to be related to the frequency of oscillation. Both of those combined are going to determine, you know, how fast you decay, which is going to be kind of related to your sigma value, right? So sigma is going to be in this axis, right? And remember, that's going to be, in this case, a function of the product of zeta and omega n. So in this case, omega n equals 1 and zeta is 0.2. So this is 0.2 and this is 0.4. So that combination of those two, right, means this is going to be e to the minus 0.4 t. Whereas for the other case, we had e to the minus 0.2 t. So that combination here is going to determine how quickly you decay. So that's why this one, for the case of omega n equals 2, is going to decay faster. So if you look at that decay, it's right. So that's e to the minus 0.4 t. Whereas if you look at omega n equals 1, you know, it's got a slower decay basically. That's e to the minus 0.2 t. Okay, so just in general, understand that where these roots are in the Laplace plane are going to determine the shape of this response. The magnitude of the pole is going to be proportional to omega sub n, and that's going to determine frequency of oscillation. And then the product of omega n and zeta is going to be related to this sigma value, which really drives how much or how fast your oscillation decays. So it's really kind of the two different things. So you can imagine, in, you know, those of you in control system design, I know you think about, well, where do I need to put my poles so that I get, you know, a desired decay value, frequency of oscillation. You know, you can kind of derive that from the design side, where you say, oh, I might need complex poles here and here. You know, that's going to give me a particular omega sub n and a particular zeta, right? Okay, so all that being said, let's kind of look at an example. This is a system, so this is kind of our G of S. It's a mass and a damper, so that looks like this right here. So all of this is kind of in our system here. We're going to control that with some proportional type controller. So we can draw a block diagram. This is our mass and damper. Come up with a transfer function, second order system. So we get this type of transfer function is our unity feedback closed loop transfer function for this second order system with proportional gain control. And let's just use an example of a mass of m equals 2, damping factor of 6, and we're going to use k equals 18 in our controller. Okay, so basically just generating some example values to give us a particular characteristic equation down here. Okay, so if we use those values, obviously we want to get this into a form that allows us to find omega sub n and zeta. So we want to divide the numerator and denominator by 2 because we want this s squared coefficient to be unity. So that gives us 9 over s squared plus 3s plus 9. Now once we have that, we know that's equal to this general form. So the first thing you can do is look at, in this case, omega sub n squared equals 9, right? So then we know omega sub n is going to be equal to 3, if we're assuming, positive, obviously. Okay, and then we also know if we kind of look at this middle term here, we know that 2 zeta omega n in this case is going to be equal to 3. So we can, now that we know omega sub n, we can solve for zeta and find zeta equals 0.5. So, kind of a system of 2 equations, 2 unknowns, not necessarily linear, but pretty easy to solve for one and then use that and solve for the other. Okay, so in this case, omega equals 3. So, if we're drawing those in the complex plane, or the Laplace plane, we would have, omega is 3, so our roots would be that, where this is omega sub n, and zeta is 0.5, so 3 times 1.5 is equal to 1.5, so that would be this distance here, right? So minus 1.5. Okay, so we'd expect this thing to decay, at a rate of e to the minus 1.5t. Okay, and this oscillation frequency would be related to this omega n equals 3. Okay, so just to kind of reference what we were drawing before. Okay, so there's the location of our 2 complex conjugate roots. And really what this comes down to is, we can take that y of t we had earlier, which was up here, which is kind of ugly, right? We can take this, and really we can use this to derive what we were talking about before as far as the 4 parameters of transient response. Okay, so if we take those, I'm not going to show the math behind it, but we can basically calculate overshoot and peak time. Okay, so overshoot is going to be only a factor of zeta, and then time to that peak is going to be related to that zeta and the oscillation frequency. Percent error is going to be related to that decay divided by this value here. That's going to give us a when it's equal to some percentage error. So if we're at 0.05 or whatever, or maybe it's 0.95, you get the idea. And then settling time is going to be, this would be percent error. So this would be like 2% or 5% or whatever we're asking for. And then settling time, we can also calculate that as well. Okay, and rise time for the second order case is it's an approximation. I'm not going to go over the derivation of it, but you can just use this general formula to approximate the rise time. 2.16 times zeta plus 0.6 over omega sub n. Okay, so that's just kind of looking at a kind of a simple curve fitting, because the actual solution of that is pretty difficult to do. Okay, so now we have all of our performance parameters that we care about in terms of omega n and zeta. which are coefficients to our characteristic equation, which is the denominator of our transfer function, right? So in this case, for our particular values of omega n equals 3 and zeta equals 0.5, we can actually go through and count all these, or calculate all these. So our overshoot is about 16%. That looks about right, yeah. So this is probably 1.163. So that gives us about a 16% overshoot. Okay, time to that peak is 1.2 seconds, which looks about right. 1.209. Settling time is 2.09 seconds, which would be, somewhere around here, which means we're kind of settling into some error. I'm not sure which percent error that's calculated for, but we could probably figure that out. I'm assuming it's maybe 5%. And then rise time is this more approximated value. Here we're saying it's about 0.56 seconds. So that's to get from 0.1 to 0.9. So that would be, this delta t here, we're saying is about 0.56 seconds. Okay? So there's a good example. So given any second order system, we can write the transfer function in terms of something like that. Once we have omega n and zeta, then we can use those values to calculate basically all four of our parameters that we're interested in a transient response. Okay? All right. All right, so that's going to wrap up the lecture on control system performance. And again, really the purpose behind this lecture is just to, you can assign values to a control system design and you'll get some response, but, how do we compare to different control systems, right? How do we compare the performance of two control systems? So we have to be able to quantify this response so that we don't just kind of look at it and say, oh, well, let's say we're comparing it to something that, has a higher overshoot, and has a different settling time. I mean, really it depends on what matters in your application. For the temperature, we don't want this to overshoot to 200 degrees. So we could say, well, if we set it to 72, maybe an overshoot of 2 degrees is fine, right? So maybe an error of 2 over 72. We want it to get there in maybe a few minutes, a couple of minutes. So we could, assign some parameters to that. So, you can compare when you design your control system, we're not really using these parameters to drive our design in this class. We're mainly using it just as a way to characterize a transient response of different controllers so that we can compare their, compare their performance. So all things being considered, you want something to respond faster. You want it to have lower overshoot. Obviously, if we wanted to do the exact response for this, we'd want it to be a square, right? Well, we know that's not going to happen in the real world with differential equations. We're not going to have some weird, discontinuous thing here, but, it would be possible, maybe, depending on the control system, to get a very quick rise and then stay at your value really quick. So, I mean, there's ways to compare these types of different control systems. So that's really what we're getting at. So I'll assign some homework related to control system performance where you can basically look at I'll give you some example systems, first and second order systems, I think, and then you can actually go through and find these parameters, calculate the transient response. Okay? All right.